Our three polynomials. Well, before we get into polynomials, I just want to cover some rules of exponents. So, you remember exponents, a to the n, where a is the base and n is the exponent, says take n a's and multiply them together. So the rules that I want to deal with these are the product rule, and the product rule just says if you have a base raised to a power and you multiply it by the same base raised to a different power, or it could even be the same power, that the result will be a, that base, to the sum of those powers, m plus n. So a to the m times a to the n is equal to a to the m plus n. So just to verify that, let's take a to the 3 times a to the 2. Well, that means take 3 a's and multiply them together. So a times a times a. A to the 2 says take 2 a's and multiply them together, a times a, which gives us 1, 2, 3, 4, 5 a's, so a to the 5th. There you go, the product rule. Next rule, power rule number 1. Power rule number 1 says that if you have a to the m raised to an n, so if you have a power raised to another power, that is equal to that base a raised to the m times n. Again, we'll use an example like here. If we have a cubed squared, that's a cubed times a cubed. Well, once we have that, that's just going to be the sum of those powers. So it's equal to a to the 6th, or if we look, a to the 3 times 2 is 6. So that's our first power rule. A power raised to a power, you multiply those powers. Power rule number 2. If you have a product, a times b, raised to a power, then that power can be distributed throughout, giving you a to the n, b to the n. Well, if we look at what that's doing, we see that that's AB times AB times AB times AB, right? Et cetera, et cetera, et cetera. Well, actually, let's do this instead. Show an example. If I have A times B to the 3, then that's AB times AB times AB. Commutative property says I can move those multiplications around, which gives me a times a times a times b times b times b. 3a's gives you a cubed. 3b's gives you b cubed. And we see ab cubed, you can distribute the cube throughout, a cubed, b cubed. Now the third power rule is the same idea, but it's division. If you have a over b to the n, that is equal to a over n to a to the n over b to the n. And again, same idea. If I have a over b cubed, that's a over b times a over b times a over b, which is equal to a cubed over b cubed. So we see that we can distribute that through. The other one, a rule that I want you to realize is the zero exponent. And I'm going to give myself, well, I'm just going to come off to the side actually. I've got the space, which is right off to the side. Any number raised to the 0th power is 1, as long as that base a is not equal to 0. 0 raised to any power is 0, as long as that power is not equal to 0. 0 raised to the 0th power is undefined. And we can see a discontinuity here because if I raise 0 to the 0th power, it's defined as 1. Nobody said that it can't be 0. If I raise 0 to the 0th power, it's defined as 0. Notice it can't be 0. So we run into the problem that these two rules would give different results if we had 0 to the 0th power. Therefore, 0 to the 0th power is undefined. You can't have 0 to the 0th power. You can't get a result of 0 to the 0th power. All right, so you're probably asking yourselves, the topic's polynomials, why are we dealing with exponents? Well, because when you're dealing with polynomials, the whole idea behind it is exponents. You're dealing with variables raised to powers. And that's the whole goal of what we're doing. So let's look at this. Well, what is a polynomial? Okay, a polynomial is an algebraic expression, which is one or more products that are added and or subtracted together. So in simplest terms. So what that could be is I may have 5 a squared b plus 7b minus 4ab squared minus 3a. So this is a polynomial. Notice that we have a product, 5a squared b, another product, 7b, another product, 4ab squared, another product, 3a, right? And they're combined by either addition or subtraction, giving us this polynomial. A polynomial consists of one or more terms. A term is one of these groupings or products, right? So this polynomial actually has 1, 2, 3, 4 terms, each one consisting of a product of constants and variables. In a polynomial, the constant part of any term is known as the coefficient. So it's known as the coefficient. And this is a multi-term polynomial with coefficients of 5, 7, -4, and -3. Now you may ask yourself, why am I saying -4 is the coefficient? Because really, what we're dealing with as polynomials is the sum of a bunch of products. When we see minus, what we're really saying is plus a negative. So this is the same as saying plus -4 ab squared. So if we have a minus combining one term with another, we'll use that and say that's negative. So the coefficient of this term is 5, coefficient of this term is 7, coefficient of this term is -4, the coefficient of this term is -3. Now, within these, we see all these terms. Well, if we're going to deal with these, we also realize that there's the possibility of having things that are like terms. Well, what do I mean by like terms? I mean you have terms that have the same variables raised to the same powers. Now in this example, we do not. We have completely different variables and power combinations. We have a squared b here, we only have b here, we have a b squared here, and we have a here. So even though we're sharing variables, they're raised to different powers and used in different combinations. Whereas, if we have something like 6xy minus 4x squared plus 3x squared minus 2xy plus 7, I now see that I have some terms that are using the same variables raised to the same power. In fact, let me use the red marker here, and I see 6xy and negative 2xy. So that term and that term are like terms. They have the same variables raised to the same power. X to the, and remember when you don't have an exponent that's really to the 1, x to the 1, y to the 1. If I go here, I have x squared. Here I have x squared. Here I have x to the 1, y to the 1. Here I have x to the 0. Right? Any number raised to the 0th power except for 0 is 1. So if we have a constant, and we would call that a constant term, then we really have x to the 0th power. Just pointing that out. But this would be the constant term. So I see that I've got xy, xy, those are like terms. You can also see that I have negative 4x squared and 3x squared. Those are like terms. X raised to the 2, x raised to the 2. And then we have our constant term over here. Let me get this out of the way just so it doesn't confuse things. So that's our constant term. Well, if we have like terms, then we can add and subtract as this polynomial states. Because we can just, you can look at this as 6xy, that's 6 apples. xy, apples. Minus 2xy, or minus 2 apples. Well, if I have 6 apples and I take away 2 apples, then I end up with 4 apples, or 4xy. If I have minus 4 pairs plus 3 pairs, x squared standing for pairs, then I have minus 4 pairs plus 3 pairs gives me minus 1 pair, x squared. And then I've got that plus 7 on the end. So we can see that I have 4xy minus 1x squared plus 7, which you may see, well, what's the use of keeping that 1 there? It's not doing anything for me. But do realize that this term has a coefficient of 4, this term has a coefficient of negative 1, and this term is the constant term, so you could say it has a coefficient of 7, or the constant term is 7. Well, continuing on with these, let's look at some single variable polynomials just to get a basic idea of what's going on here. Let's say I have 6x to the 4th plus 3x minus 2x cubed plus 1 plus 5x squared. Now we see that we have multiple terms. We have 1, 2, 3, 4, 5 terms. And we don't have any like terms. They all have x, but that's to the 4th, that's to the 1, that's to the 3, that's to the 0, that's to the 2, right? So no like terms. But what we can do at this point is, if we have a polynomial expression that does not have anything more than one variable in it, then we like to either sort them in what we call ascending order or descending order. Ascending order means that the exponents increase as we go from left to right. descending means that the exponents decrease as we go from left to right. And there are various reasons why we would choose to go either way. So let's just look at this quickly and put it into ascending order. So we start with the lowest degree variable, that would be 1x to the 0, so 1. And then we get to the next one, plus 3x, plus 5x squared, minus 2x cubed, plus 6x to the 4th. So that is written in ascending order. Notice that the exponents are increasing in value. One of the reasons that we may want to do this, and a good example of it, is regression. If you're familiar with regression, you may be familiar with linear regression or quadratic regression. They're based on a simple layout. Think of if you're dealing with a line, you have y equals mx plus b, right? But if you have a quadratic equation, you have y is equal to ax squared plus bx plus c. This will be a line, this will be a parabola of some sort. And you may look at that and go, well, what does that have to do with this? Well, if we're trying to create a regression and we don't know what degree polynomial is going to best represent it, we can start out with a generic form, y hat is equal to b sub 0 plus b sub 1 x. We're in ascending order. This is a linear equation, mx plus b. b1 is the slope, b sub 0 is the y-intercept. If we want to increase the degree of this, if we want to do a parabolic regression or a quadratic regression, then we can say b sub 0 plus b sub 1 x plus b sub 2 x squared. And notice that all we did was we added an x squared term to it. If we want to, so now we've got the parabola. Now if we want to get kind of a double curve on it, we can increase it to be b sub 0 plus b sub 1x plus b sub 2x squared plus b sub 3 x cubed. And we can keep doing that, adding higher degree terms, higher exponent terms, to better describe our equation or our relationship of data. So that's part of what we want to do with this. So that's a reason that we might go in ascending order. Generally though, the more common method would be to go in descending order, which means we start with the highest degree term and go to the lowest degree term. So in this case, that would be 6x to the 4th minus 2x cubed plus 5x squared plus 3x plus 1. So we're going from a higher exponent to a lower exponent. And this would be the general method that we would use. I would say this is the preferred method for writing a polynomial. Highest degree term to lowest degree term. When you're dealing with one variable, realize that when you're dealing with multiple variables, it can get kind of messy trying to go from the highest degree term to lowest degree term. Now, I'm using a term here that you may not understand, highest degree. Well, what do I mean by highest degree term? The degree of a term is the sum of all the variable exponents. So in this case, this would have a degree, this term, x to the 4th, would have a degree of 4. This term, x cubed, would have a degree of 3. X squared, a degree of 2. X to the 1 has a degree of 1. And this is, remember, that's times x to the 0 has a degree of 0. So those would be the degrees of those terms. But what I want to do is I want to look at a polynomial that has multiple variables in it. and I want to look at the degrees of those terms. So let's say I have negative 5x squared y z to the fifth plus 7x y squared minus 6x squared y cubed z squared minus xy z. So now I have three different variables. I have a bunch of different powers to them. Notice that I have no like terms. Even though this has x, y, and z in it, as does this and as does this, the powers are different in those. So now if I want to look at this and figure out the degree of each term, I'm going to look at the exponents and add them up. Key thing to remember with this, if you have a variable without an exponent that really has an exponent of 1, it's just given that it's 1, right? You only have one of them. It's kind of like with square roots, we don't put the 2 for the index on a square root. So if we have that, then we have 2, 3, 8. So we have a degree of 8 for that term. In this one, we have 1 plus 2 is 3. Here we have 2 plus 3 is 5, plus 2 is 7. And here we have 1 plus 1 plus 1 is 3. Remember, that's x to the 1, y to the 1, z to the 1. So 3. So we have the degree of each of these terms. Now, an additional question that I can ask with this is, not only what are the degrees of each of the terms, but what's the degree of the polynomial? So these are the degrees of the terms. The degree of the polynomial is equal to the degree of the highest degree term. So if I look at this, I have 8, 3, 7, and 3 for the degrees of the individual terms. The highest degree term is this one that had a degree of 8. That is the degree of the polynomial. So this is a polynomial with 4 terms with degrees 8, 3, 7, and 3 for each of those terms respectively. The degree of the polynomial is the degree of the highest degree term. So 8 is larger than any of the other ones, so that is our degree of our polynomial. Now, as I said, putting these in some sort of order, it could be difficult, and people may have different ideas on that, because you could say if I put it in descending order, that shouldn't be too bad. I can say negative 5x squared y z to the fifth minus 6x squared y cubed z squared, but then I have this plus 7xy squared and this minus xyz. Well, which one would come first? Does the xy squared come before xyz? That depends on what you want to use for rules for putting them in descending order. So that's why we tend to not really worry about it that much when you have multiple variables with multiple degrees. But now that we can look at them, we can determine the degree of the polynomial, the degree of the terms. We can put them in ascending order or descending order. There's a few more things that we want to take note of. First of all, poly means many. Polynomial, many numbers or many names. If we have a one-term polynomial, so it has one term to it, we call that a monomial. 1. If it has 2 terms, we call it a binomial. 2. If it has 3 terms, we call it a trinomial. If it has 4 terms, we call it a polynomial. Okay, we do sometimes refer to single-term polynomials as monomials, which to me seems like a misnomer because poly means many and mono means one. So how can you have a single-term, many-term expression? So if it has one term, we call it a monomial. If it has two terms, we call it a binomial. If it has three terms, we call it a trinomial. All of them can be called polynomials, and anything four or more we just tend to refer to as a polynomial. We don't call it a quadrinomial or a pentanomial or a hectanomial or anything of the sort. So just keep that in mind. And you'll hear these used a lot, especially considering some of the stuff we're going to get into and some of the ways that we do these things. So now that we have this, let's do some operations on polynomials. And what do I mean by operations? I mean addition, subtraction, multiplication, and division. So let's say I have 3x squared minus 7 plus 2x squared plus 4x. So I have a binomial added to another binomial, right? Two term plus a two term. I have these parentheses in place here, and that's telling me that this is a binomial and this is a binomial that are being added together. Now, if you look at this, you kind of realize, well, wait, what are those parentheses really doing for me? In reality, they're not doing anything for me. So I can rewrite this as 3x squared minus 7 plus 2x squared plus 4x. Well, why can I do that? Because that parentheses is just saying subtract these first. Well, that'll be first anyway. And these parentheses are saying to add whatever this gets to, but I can distribute adding 1 times that. So I can distribute the 1 through and I get 2x squared plus 4x. So the distributive property allows me to pull that out. And you'll notice that this is really just combining like terms. So I can do this and I say, okay, well, I've got 3x squared plus 2x squared gives me 5x squared. I have plus 4x minus 7. Well, why did I do it in that order? Why didn't I just go 3x squared plus 2x squared give me 5x squared minus 7 plus 4x? Remember, we like to go in descending order. But basically, if you're adding polynomials, you're really just combining like terms. Well, how does that change with subtraction? Let me get that out of there and make this subtraction. Well, if I'm subtracting polynomials, now I have to distribute this negative through the subtraction. So I still have 3x squared minus 7, but now I have to distribute it through, so I have minus 2x squared minus 4x. Minus 1 times 2x squared gives me negative 2x squared. Minus 1 times 4x gives me negative 4x. And once I've distributed that through, again, I'm back to combining like terms. 3x squared minus 2x squared gives me x squared minus 4x minus 7. So addition and subtraction really just get into combining like terms. If it's subtraction, you need to distribute that negative sign through the whole polynomial and then combine like terms. So that's addition and subtraction. Let's try another one here just to go a little bigger. So what if I have 4x squared minus 7x plus 1 minus 3x squared minus 7x plus 5? Okay, so again, this can just be taken out of the parentheses, 4x squared minus 7x plus 1. I need to distribute through that minus sign. Minus 3x squared minus a negative 7x gives me plus 7x and minus 5. And I'm at the point of combining like terms. 4x squared minus 3x squared gives me x squared. Negative 7x plus 7x gives me 0x, so that's gone. 1 minus 5 gives me negative 4, so I have x squared minus 4. So addition and subtraction of polynomials, pretty straightforward, not too bad. What about multiplication of polynomials? And I guess I really should clarify before I do that. Just going to put this in simple form. A plus B minus C plus D. Please take note that this is subtraction. This is very different from A plus B times C plus D. Okay, very different. These are two different things. This is not multiplication. This is not multiplying a binomial times the negative of another binomial. This is subtraction. I point this out because it's a very common mistake that I see people make. They see parentheses and they go, oh, I've got to multiply. No, you don't. That is subtraction. Parentheses side by side like this, that's multiplication. So I'm going to get rid of this top one. I'm going to stick with this simple one here. I'm going to make that parenthesis look more like a parenthesis. And the first thing I'm going to do is, if I'm multiplying binomials, I'm going to use FOIL. And you've seen FOIL before, I know you have. FOIL stands for, say it together with me, first, outer, inner, last. Which means you're going to get a sum of 4 different products. First, you're going to look at the first term in each of the binomials and multiply A times C plus. You're going to look at the outer terms in the polynomials and get A times D. You're going to look at the inner terms, B times C, and the last terms, B times D. And that's FOIL. First, outer, inner, last. And then if you can combine like terms, combine like terms. We can't at this point without putting it back into the form that it was. Let me take a step back here and say, well, what if I have x squared times 3x squared plus 7x minus 2? What would I do in that situation? Well, if you're multiplying a monomial by a polynomial, it's just the distributive property of multiplication over addition. So I'm just going to distribute this through. I'm going to take x squared times 3x squared, which is going to give us 3x to the fourth. Why 3x to the fourth? Because x squared times x squared, you add the exponents, giving you 2 plus 2 is 4. And then I multiply x squared times 7x, gives me 7, x squared times x, that's x to the 2, times x to the 1, 2 plus 1 is 3, so x cubed, and then minus 2 times x squared, so negative 2x squared. So multiplying a monomial times a polynomial, just distribute it through, make sure you pay attention to those power rules for exponents, or the product rule in this particular case. What if I multiply a couple binomials together? 3x plus 4, x squared minus 5. Remember I said that we can use FOIL, so we can do first term, 3x times x squared gives me 3x cubed. Outer, 3x times negative 5 gives me negative 15x. Inner, 4 times x squared gives me 4x squared. Last, 4 times negative 5 gives me negative 20. Now, combine like terms we can. We can't, but we can put this in descending order. So 3x cubed plus 4x squared minus 15x minus 20. So multiplying two binomials. Well, that's one way we can do this. There's another way that we can do this that will expand out to larger polynomials. Realize that FOIL only works for two binomials that are multiplied together. Binomial times a binomial, you can use FOIL. If you have a binomial and a trinomial, you can't use FOIL. So what's a method that would work if I had larger polynomials? Well, here's one method. You can create a table. What I mean by creating a table is I can just say, well, this is a binomial times a binomial. So I'm going to create a 2 by 2 grid, and I'm just going to take these terms and make them the headers to each of these columns or to each of these rows. So I have 3x plus 4, I'm going to call this 3x, and I'm going to call that 4. I have x squared minus 5, I'm going to call this x squared, I'm going to call that negative 5. Now I can fill in each of these grids by performing the multiplication. X squared times 3x gives me 3x cubed. X squared times 4 gives me 4x squared. Negative 5 times 3x gives me negative 15x. Negative 5 times 4 gives me 20. So now I have filled those in, and I can just pull this out, combining like terms as I do so. No like terms in this. So I get 3x cubed plus 4x squared minus 15x plus 20. And the nice thing about this is that it's expandable. So if I had a trinomial, I would just have an additional column or additional row. So let's take a look at that and verify that. Let's turn this into a binomial multiplied by a trinomial, 5x plus 6. So now I have a binomial, 3x squared plus 4, multiplied by x squared minus 5x plus 6. Now, we can't do FOIL because we've got this random term in there, so that's not going to work. So we can use our table, and we're just going to do 3 columns and 2 rows. Now you may ask me, why did I put the 3 columns and 2 rows instead of 2 columns and 3 rows? Personal preference, but in general this is the way you'll see people do it. It's easier to work with the table being wider than it is taller rather than working with it taller than it is wide. Just the way it works. So if I'm going to do that, so I've got my trinomial up here. Remember, commutative property multiplication says it doesn't matter whether I have this multiplied by that or that multiplied by this. Which order you multiply, it doesn't matter. So I've got x squared, negative 5x, 6, 3x, positive 4. So now I can go through 3x times x squared gives me 3x cubed. 3x times negative 5x gives me negative 15x squared. 3x times 6 gives me 18x. 4 times x squared gives me 4x squared. 4 times negative 5x gives me negative 20x. And 4 times 6 gives me 24. And now we're going to add them up while combining like terms, and we see that I've got 3x cubed. I've got negative 15x squared, and I've got 4x squared, which gives me negative 11x squared. I have 18x, and negative 20x gives me negative 2x. Sorry, I got carried away there. And then plus 24. Now, some of you may have noticed that the like terms ended up in diagonals. The answer is no, it does not always turn out that way. It depends on what you're what your polynomials are that you're working with. Sometimes it works out that way, and that's handy. Sometimes it does not. It can depend on whether you're missing a degree along the way. Notice this was x and x to the 1 and x to the 0. if this had been x squared next to the 0, then that would have thrown off the multiplication and it would not have necessarily ended up being a nice diagonal for that. So you just have to look through and see if you have any like terms. So that's a second way that you can do multiplication of polynomials. A third way, and I'm going to use this to demonstrate it. Now this is one that it works, and if you're consistent in what you do, it can work very well. But you just want to be careful because it's very easy to lose some of your terms while doing it this way. I call this multiple distributions. If you look at this, you realize that if I get rid of that, then I just have 3 times x squared minus 5x plus 6, which is just distributing. If I get rid of this, I have 4 times x, which is just distributing. And what FOIL really does is it really is just distributing multiple times. With FOIL, remember it was a plus b times c plus d. You could look at it as what it's really doing is it's distributing through the first term through the second binomial, right? A times c, the first terms, a times d, the outer terms, and then it's distributing the second term through b times c, the inner terms, and then b times d, the last terms. So all it's doing is it's just distributing the a through there, and then it's distributing the b through there. So I can do the same thing with any size polynomials that I can just distribute through. I can just look at this and say, well, that's 3x times x squared is 3x cubed. 3x times negative 5x gives me negative 15x squared. 3x times 6 gives me plus 18x. And then distribute this one through plus 4x squared. 4 times negative 5x minus 20x. And then 4 times 6 is plus 24. And then I can combine like terms while putting it into descending order. And I get 3x cubed minus 15x squared plus 4x squared gives me minus 11x squared plus 18x minus 20x gives me minus 2x and then plus 24. And you'll see that that came out to be exactly the same as when we used the table to do it. So a few different choices. If you're dealing with, if you're dealing with a monomial times a polynomial, you're just distributing through. If you're dealing with something larger than a monomial multiplied by something larger than a monomial, if it's 2 binomials, then you can use FOIL. You also have the option of using the table and doing your multiplications there. And if you end up with something larger than a binomial in the multiplication, so larger polynomials, you can use the table or you can just keep distributing through. The one thing you want to keep in mind if you choose to distribute through is that you don't want to lose any of your products. And that's a common thing, especially when you get into larger polynomials multiplied by larger polynomials. It's very easy to lose one of your terms while you're working your way through. So safest bet may be to use the table method because then you're guaranteed not to lose a term because as long as you filled in all the spaces in the table, you've done all your multiplications. The other thing you can do is realize that the product of the number of terms will tell you how many terms you should have once you've multiplied through. Here I have 1, 2 terms. I have 1, 2, 3 terms. 2 times 3 is 6. So I should have 1, 2, 3, 4, 5, 6 terms when I'm done multiplying. So if I had a polynomial with 5 terms multiplied by a polynomial with 6 terms, then I should have a resulting polynomial with 30 terms, 5 times 6, before combining like terms. So you should end up, if you're doing 5 terms times 6 terms, you're gonna have 30 term result, which then you'll combine the terms. And that's multiplication.